Hello everyone, this is Vasilis from fall 2017, and this is a Data 8 probability review in preparation for Midterm 1. So what we're going to do in this video is we're going to go over some probability questions that we have over here for you, and then we are going to discuss some of the concepts that have come up in lecture and that you're going to have to deal with in the midterm. So let's zoom in a little bit more first. Okay, so let's dive into the problem. So usually what I do whenever I look at a probability problem is always try to keep track of the important things that are going on. So let's get started with that in mind. So I have a jar that contains 100 jelly beans that have 4 different colors: orange, green, blue, and purple, and they all appear in equal amounts. So what I'm going to keep from this is that I have orange, green, blue, and purple ones. And since they all appear in equal amounts, then I'm going to have 25 of them for a total of 100 jelly beans. Now, the first question that we have is that Wilton likes green jelly beans specifically, and he picks 5 bins at random without replacement. So here the important information is that we have sampling without replacement from the jar. So the question that we have is, what is the chance that he gets a sequence of all green beans? So there are a couple of things that we need to remember here. So this is a problem that asks us to calculate the probability of a particular sequence. In this case, this particular sequence in which we're going to get green jelly beans in each draw from the jar. Whenever I see a question like this, the first thing that I think about is it possible for me to calculate the individual probabilities in each separate draw of the sampling process, and then use the multiplication rule? So use the multiplication rule that we learned in class in order to chain these probabilities together and get the final result. Okay? So what I'm going to look at first is, what is the probability that in the first draw I get a green bean? And then I'm going to multiply that probability with the probability that in the second draw I also get a green bean, given that I got a green bean in my first draw. And then I'm just going to keep going on until my sequence is complete and I have all the probabilities I need. Okay, so let's start calculating these probabilities. So in the original problem, remember that the implicit assumption here is that I have an equal chance of picking out any one of the 100 jelly beans that I have in my jar, which means that we can employ the strategy of finding the probability of getting a green marble by counting the number, or a green jelly bean, excuse me, by counting the number of green beans at any point throughout our sampling process, and then simply dividing by the total number of beans that we have left in the jar. Okay, so I'm using these two ideas that we have talked about in lecture, and let's see what we get. So for the first sample, I have 25 green jelly beans, and I can pick whichever one I want from these, and I have 100 jelly beans total in my jar. Now for the second draw, I see that Wilton is sampling without replacement, meaning that after he draws a first green bean, for the second sample, we're going to slightly change the setup of this problem so that there are 24 green beans left in the jar. Okay, so now by following exactly the same process of counting the number of green beans remaining, I see that I have 24 green beans because I'm sampling without replacement. So I'm not putting back the green bean I sampled in my first try. But at the same time, the total number of beans has decreased down to 99. But now I can see a pattern of how I'm going to solve the rest of the problem. Now I know that after I sample 2 green beans, I know that there are only 23 beans left in my original jar, for a total of just 98 jelly beans. Okay, so if I keep going on with this approach, I am going to get this nasty probability. So just to recap what I did. So first I noticed that this was an experiment in which I was sampling without replacement. Hence, I wasn't putting back in the marbles that I drew from my jar. And then I realized that this is a sequence problem in which I'm going to calculate each individual probability of getting a green jelly bean at each draw. And then I'm going to multiply all those individual probabilities together because I want to make sure that the first sample is a green bean as well as the second one as well as the third one. Okay, so I'm going to so I use the multiplication rule for that. So this idea is actually it works fairly nicely in other problems as well. So let's see what we can do with the second one. So in this second problem, Wilton replaces the previous bins. So we have a stored setup of 25 beans for each color. And then what he does is that he picks another 5, this time with replacement. So remember that our problem is slightly different now. And what we're asked to calculate is the probability that he gets at least one green bean. So now the piece of information that you need to remember from lecture is that some problems are particularly hard when we are trying to calculate them one way. But sometimes when we look at their complement, they become significantly easier. So let me explain to you what I mean by that. So suppose that we want to calculate the probability of event A happening, which I will denote by P of A. But now I know that the probability that event A doesn't happen has some probability. Let's call this P prime of A. So A is the probability of event A happening. A prime is the probability, P of A prime is the probability that event A doesn't happen. And I know that the sum of these two probabilities always needs to be 1. So now, if this is what I'm trying to calculate, we see that I can either try to go for it and calculate it directly, or I can try to calculate this quantity here, which we refer to as the complement event, the complement of A. So in our particular case, we want to find the probability that in 5 draws, Wilton has drawn at least one green bean. However, this is a somewhat hard probability to calculate. And the reason for it is that there are many possible sequences. So if you try to put some thought into how you can sum across the probabilities of all those sequences, that's going to take a lot of time and effort. So we need to find a better way to do this. So now let's try to look at what the complement event, what P of A prime is for this particular problem. So if Wilton needs to calculate the probability that he gets at least one green bean, the complement of that event needs to be that he gets no green beans. Because if he has at least one green bean, then the probability of A is the event A has happened, and we're referring to this probability P of A. So now P of A prime is the probability that Wilton doesn't draw any green beans. And this is significantly easier to calculate. So using exactly the same ideas that we used in the previous problem, namely the counting approach to calculating probabilities, as well as the multiplication rule, we want to see what the probability of getting a sequence that has no green beans is. So now let's look at the first try. So since I don't want to get a green bean in my sample, I see that I have 75 potential favorable outcomes that I can get that satisfy the potential sequence I want to have in the end. So this probability is going to be 75, the total number of outcomes, divided by 100, the total number of options that I have when I'm picking a particular jelly bean. Now, in the second trial, I know that Wilton is sampling with replacement, which means that whatever jelly bean he has drawn in the first trial, he's going to put it back in the jar before he samples any more from it. So now that probability needs to be 75, but again, since the number of marbles hasn't changed because I'm sampling with replacement, I'm gonna have exactly the same probability here. And then I'm going to keep going for all 5 tries, which is going to give me a probability that my complement event is going to be 75 over 100 raised to the 5th power. And now I can calculate the original event that I was going for, namely the probability that I get at least 1 green bean, by using this formula I wrote right here, which is going to be that probability of A is equal to be 1 minus probability of A prime. So 1 minus 75 over 100 to the 5th. Okay, so this is the second problem. Now moving on to the last sub-question. So now Wilton draws 4 bins without replacement, so the problem changes again, and we're asked to find the chance that all 4 bins have different colors. So again, you are thinking that we have 4 possible samples that we need to take, and we have sampling without replacement, meaning that the total number of samples is going to decrease every time we take, the total number of jelly beans in the jar is going to decrease every time we take a sample. So now the way to think about this is that, do we really care what the first jelly bean that we sample from the jar is going to be? And the answer is no. And given that I don't have any idea of what the other jelly beans are, the first one might as well be each one of the possible colors that I have in my jar, namely green, purple, orange, or blue, which tells me that this probability is going to be 1, simply because I can sample anything from the jar and I'm still not going to violate any of the requirements that I have in this problem. So now for the second sample that I take from the jar, the situation is slightly different. And the reason is that instead of having 100 marbles, so here I'm going to track the total number of bins. I'm sorry. So the first trial I had 100, but now I know that I have sampled one bean, which means that I'm going to be left with a total of 99 beans. And what I also know is that I have 24 beans of some color that I have already drawn, and I have 25 beans for every other color that I haven't seen yet. So now, since I want to sample something that is not what I got in my first trial, then that means that I have 75 possible options, like 25 for each color that I didn't draw in my first trial, divided by a total of 99 beans, which is the total number of beans that remains in my jar. Now, in the third case, notice that the total number of bins is going to be 98, but at the same time, I'm going to have 24 for each one of the 2 colors that I've seen so far, and I'm going to have 25 beans from each color that I haven't drawn, okay? So now for my third trial, I need to sample some color that I haven't seen before, so my total number of options is going to be 50, divided by the total number of beans remaining in the jar, which is going to be 98. And finally, at this point in the experiment, I have seen 3 different colors. So I need to sample 1 bean from the jar that is going to be from the 1 color that I haven't seen so far. So I have 25 options for that color, and out of a total of 97 beans that are remaining in my jar. So if I multiply all of these probabilities together that I have calculated for each trial, I am going to get the total probability that Wilton is going to sample 4 beans of different colors without replacement. So that's it for this exercise. Thank you.
Hi, my name is Tanay. I'm a TA for Data 8 Fall 2017, and today we'll be covering a question about rolling 2 dice and basically wanting to calculate the probability of the sum of these few situations. So I'm currently going to write out a table basically that illustrates the number of basically outcomes, or each individual outcome that is possible from rolling 2 dice. So in our problem description, we basically have Alex and Weston. They decided to roll 1 dice each, and they want to calculate the probability of each event. And if we remember, basically, the probability of the events, or of an event, is the probability that it occurs over the total number of possible outcomes. So in our case, there's 6 sides to a dice, which means that if we want to roll 2 individual times, then the probability is just multiplying 6 by 6, or the total number of outcomes, sorry, is multiplying 6 by 6, which is 36. So in each one of these cases, we have a different thing that we want to accomplish. Basically, they all look very similar. We're just wanting to calculate the sum of 2 things, but the way to approach each individual section is very, very different. So now that the table is written out, we can actually start this question. So we want to calculate the probability that the sum of 2 dice rolls is equal to 1. So this is a fairly simple problem. It's just an equality. So what we want to do is we want to calculate, basically, we want to find the number of outcomes that this happens over the total number. As we established before, the total number is 36. So let's write 36 down here. So we know that now we have to find all the possibilities that 2 dice rolls will equal 1. So we already have all possible events in our table. So let's just try to find the 1 in here. And as we can see, we can't find a 1. We can see the smallest number from 2 dice rolls is 1, so we just put a 0 here, and the probability as a result equals 0. So now we have this other probability where it's equal to 4. So we basically do the same thing here. We have the total number of outcomes, that's 36. We have to find the number of 4s that equal it. So we don't count like the 4s on the side, but basically we just calculate anything inside this little box. So as you can see, we have 1, 2, 3, 4s just right along this diagonal. Looks like a little word search here. So we have 3 over 36, and that's basically just 1 over 12. So now this is a little bit different. We have less than 9. So as we can see, there's a lot of cases that are less than 9. We can see like along this diagonal right here, this is where 9 and greater than 9 is basically here. So we have a lot of cases basically of numbers being less than. So there's 2 ways we can approach this. You can either just like count up every single one as being less than 9, and that will also give you the same answer as the more easy method, basically. The more elegant way to solve this question. So what we can do is we can actually take the complement. We've talked about the complement earlier on in this video as well, but we can basically take the complement and we can say that the probability is 1 minus the probability of 2 dice rolls being greater than or equal to 9. As we remember, basically, this is just saying the opposite of that 2 dice rolls is less than 9. So we can say 2 dice rolls is greater than or equal to 9. And this is a lot easier to find. If we like cross out this part, we just have to count the number of 9s, 10s, 11s, and 12s, which is a lot easier to do than counting 2, 3, 4, 5, 6, 7, and 8. So let's actually do that. So let's add up all these individual probabilities. So we have 1 minus, and as we remember, we have 1 minus the probability of having 9s plus the probability of having 10s plus the probability of having 11s and the probability of having 12s. So the probability of having 9s, that's the first thing we want to do. That's 4 over 36 because there's 4 9s. Then we're going to add 10s, 3 over 36. We're going to add 11s, which is 2 over 36. And then there's 1 12 over 36. So what we do now is that we add these up. So we have 4 plus 3 plus 2, that's 9, 10. So we have 1 minus 10 over 36, which is then, 1 minus 10 over 36. So if you remember that, which will just give us 26 over 36, which, if you want to simplify this down, is just 13 over 18. So as we can see, we basically kind of figured out a little bit about this probability distribution. We also have the number of counts possible. But let's say we want to find an empirical distribution that kind of matches what we know about this probability distribution outlined by the table. So let's figure this out using sampling. So let's state the goal right now. So I have this initial table right here, or this initial basically bar chart right here, and basically that will just give us each probability at each possible sum. As we can see, it's very even on both sides. It's split right down the middle at 7, and this is the goal of our next exercise. We want to get basically a bar chart that looks exactly like this. That is our goal. So let's try to figure this out. So as we remember in previous labs and previous lectures, we like to use this magic number of sampling being 10,000. Why do we do this? So we do this because of the idea of law of averages, which states that as we have more and more experiments, or more basically experiments run under the same conditions and doing the same things, they'll kind of converge to the probability distribution. So when we have 10,000 samples, this is what we consider a decent amount for our purposes in order to kind of mimic our probability distribution. So let's start with there. So we've currently loaded up an array representation of a dice, which is basically an array with 1 through 6, and you can just basically pick and choose all the numbers you want, right? Or you can, in our case, we'll randomly choose them because that is what our purpose is. So as we remember, whenever we do a sampling problem, we want to start with a for loop, because when we do a for loop, that allows us to have the key component of the law of averages, basically saying that every experiment or every individual experiment must be the same. And this is a way for us to control that. So you can say dice 1 is the random choice of selecting from dice. And dice 2 is another roll, which is what we mimic by saying np_random.choice from dice. So now we want to get the sum of the rolls, which is just dice 1 plus dice 2, which is again what we're doing in our head, or in the case on the table, to find the true probability distribution. So let's basically want to store all our results into an array. So we can just make an empty array. And let's append all the results that we have in this for loop onto this array. And we can take a little peek into our results. And so in terms of the preview we get, those look pretty good to us. We have 6, 10, 7, 5, 4, 11. In terms of what we saw in our table, those all exist. So we can say initially that this looks fine. Now we can put this into a table, and we can just start graphing stuff out. So let's put these as just something called rolls, and we can just put our results in there. And then we can, again, the table should just basically look very similar to our original thing. As you can see, it probably looks almost the same, and we have 10,000 rows in there, so that's good to go. Now, what we want to do is we want to count the number of times they exist, because our empirical distribution has to be very close, which means that we want to find out the number of counts in each situation. So let's call this empirical dist. And let's group by the number of roles we have. Oops. And let's show all of the roles. I think they're 11, yeah. So now we have each one of the counts of the roles, and we can see that it kind of looks, if we just like eyeball it right now, it looks very similar to what we have over here with the probability. But the way we want to actually display that is, again, through this bar chart. So let's make this bar chart real quick. If I remember what I named this table, empirical dist. Then we can just take the bar of the roles and the count. And we can see that it looks very similar, but it's a little bit like weirdly adjusted. It's like a little bit higher on 6 compared to like 8. And it's not like perfectly even, which of course is what is to be expected, because this is empirical. And the whole difference is that like this is generated from experimentation and from basic sampling. So let's try upping the number of samples we have, because if we take the law of averages, the more sample number we have, the more closely it will start to resemble the probability distribution. So if you run basically everything again, and then wait for this all to complete, scroll down to the bottom, we can see this very much closely mimics the structure of our original probability distribution of the sum of 2 dice rolls. As a result, the more this kind of like concludes what we're talking about with sampling, in that the more trials you have and the more samples you take, the more likely it will converge to the probability distribution. And this is what we're trying to stress here, is like we have all this empirical data and we need to find the underlying distribution, and sampling is kind of a way to help us. Thanks.